In the last video, I talked about incorporating nonlinear relationships into multiple linear regression through the use of transformations. In this video, I'm going to talk about using interactions between predictor variables in the model. So, to motivate this, we're going to use an example where we can see everything that's going on in a scatter plot. And so we're going to have two predictor variables, and we're going to suppose that the association between one predictor and the response variable varies according to the value of another predictor. And the way that we can model this in the regression model is to add the term x1, x2 in our model, where the value of x1, x2 for each sample observation is simply the corresponding values of x1 and x2 multiplied together. So the running example will use sales data where the response variable y measures annual sales, and we've got two predictor variables. X1 will measure the annual spending on advertising in millions of dollars, and x2 will measure the prevailing interest rate in percentage. And as an example of how this could arise is, let's suppose that sales were to increase on average by $1.58 million for each additional $1 million we spend on advertising when the prevailing interest rate is 2%. But if the interest rate was 5%, then that expected increase in sales comes down to $1.21 million. So this is an example where the association between sales and advertising depends on the value of the other predictor, the interest rate. So let's look at some actual data. So I've got my sales 1 data, and I'm going to draw a picture. So here's my data, and let's see. Yeah, that just about works. Let me make this bigger. Okay, so what have we got going on here? So what I've got here is I've got my x1 predictor on the horizontal axis and my response variable y on the vertical axis, and then I've marked the points according to the interest rate, which is the other predictor x2. And so, for example, with an interest rate of 2%, though we've got three values there, so there's an increase in expected sales when advertising increases, and the interest rate is 2%, and it's given by this relationship between these three points here. When the interest rate is 3%, the relationship is given by these 3 points here, and when the interest rate is 4%, it's these 3 points here, and when it's 5%, it's these 3 points here. And so the question we're asking is, does the association between sales and spending on advertising, does that change according to the value of the interest rate? So it's kind of hard to tell from the graph if that relationship changes or not. And so what I mean by does that relationship change, what I'm really asking is if I was to draw a regression line for an interest rate of 2%, and another regression line for an interest rate of 3%, and another regression line for an interest rate of 4%, and another one for 5%, would those regression lines, would they be parallel, or would they have different slopes? If they're parallel, then there's no interaction, and if they have different slopes, then there's interaction, and the relationship between sales and advertising is changing according to the value of the interest rate. So I've got a picture here of that same graph that I just looked at, but I've added those regression lines that I'm talking about. And the question I'm posing is, what are the slopes of those regression lines for each interest rate? So how do I get these lines with different slopes? So it turns out I can get lines with different slopes by fitting this interaction model. Okay, so I mentioned this interaction term, which is multiplying the two predictors together. And all I do is I create this as a new variable in my data set, and then I add that as a predictor, as a third predictor, if you like. And so then if I take this equation, so this represents the expected sales for particular values of x1 and x2. If I note in my data set, x2 either takes the value 2 or 3 or 4 or 5. Let's simplify this equation to see what this equation looks like when x2 is equal to 2. So when x2 is equal to 2, I'm going to plug in 2 here and 2 here, and so I'll have b0 plus b1 x1 plus b2 times 2 plus b3 times x1 times 2. So I can rearrange that by putting the b0 and so this piece and this piece together. Remember, x2 is 2 here, so that's just numbers. b0 is a number, b2 is a number, so I could add b0 and 2b2 together to get another number. And then the other piece is I've got b1 times x1, and I've also got b3 times x1 times 2, or if I rearrange that, I've got 2b3 times x1. Okay, so I've got this part of the equation as well, b1 times x1 and 2b3 times x1. If I pull x1 out as a common factor, I've got b1 plus 2b3 times x1. So if you think about it, this is a function of x1. There's, if you like, an intercept and a slope. Okay, I could do a similar procedure by plugging in x2 equals 3, and I would get this is the new intercept and this is the new slope. Okay, and then do the same for x2 equals 4 and x2 equals 5. So what I've done here is I've simplified my model and created 4 equations. One for x2 equals 2, one for x2 equals 3, one for x2 equals 4, and one for x2 equals 5. And they're all equations of a straight line with respect to x1. And each one has a different intercept and a different slope. Okay, and in my picture here, I've drawn these 4 lines on my graph. Okay, so this line here going close to the points marked 2 is this equation. Okay, and this line here going close to the points with a 3 is this equation, and so on. So I've got 4 lines all with different intercepts and different slopes. Okay, and if I look at the equations of the slopes, these are all going to be numbers. B1 is, well, we're going to estimate them in the sample, and when we do that, these will be numbers, and these will be different numbers as long as B3 is not 0. If B3 was 0, this piece would go away, and this piece would go away, and we'd be left with B1 in all cases. So the thing that makes these lines have different slopes is if B3 is not 0. So in other words, if we were to look at that regression parameter and maybe do a hypothesis test for it and reject the null hypothesis that B3 is 0, then we would have shown that we would expect in the population that these 4 lines have different slopes, and we would have shown a significant interaction effect. Okay, so that kind of motivates what we're going to do next. So what we're going to do is we're going to create that interaction between advertising and interest, and then we're going to fit the model. So I've got advertising, interest, and the interaction. And then if I summarize the model, and then I'm interested in doing the hypothesis test for whether the regression parameter that goes with the interaction term is 0. And to do that, I'm going to look at that test statistic and look at this p-value, and if that p-value is smaller than our significance level, then we'll reject the null hypothesis and conclude that we do have a significant interaction effect here. And then what I can do is I can look at these numbers. Okay, 5.941, 1.836, minus 1.312, and minus 0.126. Okay, and that's going to be my fitted equation for predicting sales based on values of x1 and x2. And then I can think about, well, what does that equation simplify to if I plug in different values of x2? So for example, if I plug in x2 equals 2, what does this equation simplify to? Okay, so let me do that. Okay, so here's that equation for the predicted sales, and I'm going to rearrange it so that I move this piece with x2 next to the 5.941, because this is just going to become, when I plug in x2 equals 2, this is just going to become a number, and this piece has got x1 in it, and this piece has x1 in it, so I'm going to leave these two pieces over here, and then I'm just going to bracket off the different pieces. So 5.941 minus 1.312 x2, that's going to represent my intercept of my line when x2 is fixed at a particular value, and then this will represent my slope with respect to x1 when x2 is set to be a fixed value like 2. Okay, so let's try that. Let's plug in x2 equals 2 to this equation. Okay, so I've got this. This is a number that I can calculate, and this is a number that I can calculate. Okay, and I'm actually going to switch over to R now so that we can do that calculation. So that's these two pieces of code here. What I'm doing here is I'm taking 5.941 minus 1.312, and then I'm multiplying it by, I'm going to do all the calculations at once. So I'm going to multiply it by 2 and 3 and 4 and 5, and then the answers I get for those calculations are 3.317, 2.005, 0.693, and minus 0.619. So that's the result of this calculation when x2 equals 2, 3, 4, and 5. And then, so that these are the intercepts, and then the slopes is the other piece of the equation, 1.836 minus 0.126 times 2 and 3 and 4 and 5, and I get these numbers, 1.584, 1.458, and so on. Okay, so let's just go back here and keep going. Okay, so the 3.317, that's down here in the calculation that I did in R, and then 1.584, that's this number here. Okay, so this is what this equation simplifies to when x2 equals 2. When x2 equals 3, I get this, so 2.005, and then 1.458, and then x2 equals 4, I get these numbers, 0.693 and 1.332, and finally, oops, that's a mistake there, when x2 equals 5, I get minus 0.619 and 1.206. Okay, so these are the equations here and here and here and here of these 4 lines. Okay, and I can reproduce those in R. By doing this. There we go. Okay, so there's a pictorial representation of my model, and I can do this because I've got a simple example where I've got one predictor that I can put along the horizontal axis, and my other predictor just takes on 4 discrete values. So I can draw 4 discrete lines for this example. Okay, so I went through quickly the hypothesis test that tells me that I've got 4 lines with different slopes, and the way that we did that was to look at this p-value here and determine that since the p-value 0.012 is less than the significance level, we reject the null in favor of the alternative, and conclude that we do have a significant interaction effect. In other words, the association between advertising and sales does appear to depend on the value of the interest rate. Okay, let's look at another example. So in this data set, this one is similar, only we have sales again, y equals sales again, x1 is advertising again, but this time x2 is a count of the number of retail stores that the firm has. So I think it starts off with 1 store, and then it grows to having 2 stores, and then 3 stores, and then 4 stores. And so what is the relationship between sales and advertising? Does it depend on the number of retail stores? Okay, so this is what my data looks like. So let's have a quick look at that in R. So I'll draw my data. I'll put my points on. Okay, I'm gonna skip the legend in this instance because it just kind of gets in the way. And here's my 4 regression lines. And the question is, do I have evidence of non-parallel lines here? Does it look like the line? These are the sample lines. The sample lines will always be non-parallel, but the real question is, in the population, could those lines be parallel? Okay, so to do that we need to do the hypothesis test. So here's my coefficients table, and here's my p-value for the interaction term. It's larger than my significance level, and so I fail to reject the null hypothesis. So in other words, the regression parameter that goes with the interaction term could be 0. And so if it's 0, that would mean that these 4 lines are actually parallel in the population. Okay, so the association between sales and advertising in this case does not appear to depend on the value of the other predictor, number of stores. Okay, so if that's the case, then this term shouldn't really be in the model. It's not significant, and it's actually making things more complicated than they need to be in the model, and I'm better off removing it from the model. So that's what I should do. I should go to a second model where I don't have the interaction term, and this will be my new model. So this is my new model, and this is my regression equation. Okay, I'm getting that from these numbers, my coefficients table. Okay, and and again, now I could do the same thing I did before. I could plug in x2 equals 1 for the predicted sales equation when the number of stores is 1. I could plug in x2 equals 2 for the predicted sales when the number of stores is 2, and so on. So again, I could get 4 different equations for the different values of x2 and simplify. So for example, when x2 equals 1, what would happen here? Well, I'd plug in 1 here, so I'd get 5.65 times 1, so that's just 5.65. And if I do 5.65 and combine it with the minus 4.77, I get 0.88. Okay, and then the 1.05x1 is just there's no simplification that I can do there. That's what it is. Okay, so this is the equation of the regression line for when x2 equals 1. Gives me a way to predict sales when x1 for a particular value of x1, given that x2 is equal to 1. I could do a similar thing for x2 equals 2, and x2 equals 3, and x2 equals 4. And if you think about it, let's do x2 equals 2. So I'd have 2 times 5.65, and then combine that with the minus 4.77. That would give me an intercept. But the 1.05x1 there's nothing I can do there. There's nothing to simplify. It's just going to be the same. So for all 4 equations, I'm going to have different intercepts, but all the slopes with respect to x1 will be the same. Okay, so coming back to my picture, it's meaning that all these lines have the same slope. They're all parallel. Okay, so that's a couple of examples of the first example. We had a significant interaction term, and that gave me a relationship between y and x1 that changed according to the value of x2. And in the second example, the relationship between y and x1 with respect to the slope stayed the same for all the values of x2. Okay, we had the same slope for each of my lines. So in general, in more complicated examples with multiple predictors, we're not going to be able to necessarily look at nice simple graphs like this that show us what's going on, but the same principle applies. So we can add an interaction term to our model and test it to see if it's significant or not. And if it's not significant, we can drop it from the model. Whereas if it is significant, then it has value in our model. Just as with polynomial regression, I talked about retaining hierarchy, and that meant if I have x squared in my model, I'll include x by itself as well, regardless of its significance. There's a similar idea with interactions. Often when we've got x1, x2, say in a model, then we often include x1 by itself and x2 by itself, regardless of their significance as well. So again, that's called retaining or preserving hierarchy. How do you do this in practice? So again, just as with the use of transformations, it's good if we have some background knowledge that is suggesting to us that we ought to include an interaction between particular predictors. In the absence of that, there might be a little bit of trial and error involved. You might suspect that there may be an interaction between two predictors in the way that they are affecting the response variable. So you could create that variable in the dataset, try it in the model, see if it's significant. So again, it's a bit of a dance that you're doing here. You're wanting to include things that are going to benefit the model, but you're not wanting to make things overly complicated. So, although this allows you to model quite complex relationships, those aren't necessarily always going to be a good thing, because again, you don't want to be overfitting your sample and struggling to generalize to a population, and you're also not wanting to make the model overly complicated so that you can't end up interpreting it. So a balance has to be struck here. So that's a discussion of interactions, and in the next video I'm going to talk about incorporating qualitative predictors into a model. So everything we've talked about up to this point in the course has involved quantitative predictors. So predictors where the variables have values, and those values have meaning. They're measurements of things, and the numbers are meaningful. So it's also possible to include qualitative information, so information, for example, such as gender, or the different types of degrees that people have. So things like that are qualities, and they don't have numbers associated with them that are measurements of things. And so we'll discover how to incorporate that kind of information in a multiple linear regression model.